Hello, friends. Really excited to get to spend a little more time with you today. Um, I wanted to share a couple of quick thoughts with you on Big O notation. Now, um, Big O notation basically explains, all right, worst possible case as we make the size of the problem that we're dealing with nearly infinitely large. Um, as as we continue to get bigger and bigger and bigger, how is the time complexity of this problem going to grow? So that's my rough understanding of it as of today. Now, I feel like there's a lot of people who have done a lot better job of explaining that. And so I wanted to share with you just a little bit of that. So I'll go ahead and share my screen with you so you can see what I'm looking at. I'm working in Hyper-V again. I've got a document. One of the documents I'll be working with is notes on Big O. I put this in my class module sometimes as a separate file. This is also part of my syllabus for my handbook for my algorithms class. So anyway, um, for for right now, you can find it under modules. Okay, so let's get started. I'm working out of Daniel Lang's book, and so the PDF on the screen is the 10th edition, I think. We're on the 12th edition as of today. Um, Excellent book, excellent reference. I would highly encourage folks to get their hands on a copy of that. So, chapter 22, developing efficient algorithms, and they talk about lots of things. One of the things they say is asymptotic growth or asymptotic analysis. Basically, what that means is let's let's only consider the parts that grow as this problem gets really, really big, and let's not worry about some of the other details. Okay, so Big O notation, and like I said, um, Daniel's got a good explanation. I've got I've got several other textbooks. Here's one that talks about Big O notation, and they've got a slightly different explanation for it. See if I can bring that up right quick. Um, so for a given complexity of a function, f of n, the order of the function is the set of complexity functions g of n for which there exists some positive real constant c and some non-negative integer n, such that for all sets greater than or equal to n, the function g of n is less than or equal to some constant, real constant c times a function of n. And so some of the definitions and some of the explanations are a little more straightforward and easier to understand. Some of them are a little more difficult to understand. But the point that I'm trying to make is there's a lot of people that have looked at it, and sometimes you get a very nice brief introduction, and that's what Daniel provides in here. Now, somewhere in the reading, he actually points out this is a brief introduction. And the reason he points that out, he actually, if you come back to the appendices, they've got an appendix. Okay, so in the later versions, he actually has a even more detailed discussion of Big O notation that he pulls out into the appendix. So worst case analysis is easier to perform, so the analysis generally considered for the worst case. And he does a good job of explaining what on the order of n means. And so what he is explaining here is, listen, it's a growth factor as you're, the multiplicative constant have no impact on the growth rates. So for a growth rate of n over 2 or 100n is the same as for n. So these are all what they call linear growth. And so Daniel does a little bit more explaining, and then he says, all right, let's get into some examples. And this is the part that I really got excited about, because this is something I can start to get my head around. Daniel says, all right, look at this for loop. So every time for every n, we're going to do something. And so the constant time c is for executing this step. Every time it's the same step. And since the loop is executed n times, the time complexity for the loop is a constant c, which is the time that it takes to do this, times n. So we get linear growth. Constant growth, they give the example of looking up an array. Looking up a single item in the array that you know where it exists already. So that's on the order of 1, and then this is on the order of n for a for loop. And then Daniel says, hey, let me give you some code. And so the code that he gives us is get time for doing it this many iterations, this many iterations, this many iterations. And every time there's about 10 times as many iterations. And so what we see, 6, 61, 610, 648. One of the things they talk about is how difficult it is to actually get those kind of numbers on a computer. So what I did is I came in to Eclipse, and which is my integrated development environment. This is Daniel's code. And notice how it's copy, paste, copy, paste, copy, paste. My good friend Uncle Bob says that if you're doing copy, paste a lot, you're probably doing something wrong. So what I did was I dropped this into a for loop. And my for loop index is size. And so then I still have the function get time. And then inside get time, I do the same thing as Daniel. So I've got start time and I've got end time, and then I've got these little nuggets in here. So linear example time of n. And so I literally had just copied, and so I used the same variable n that they had used here. And so here's the linear time example, and we can, oops, swing and a miss, sorry about that, friends. We can pop up here. I'm gonna, that should work. No. Get time, and we'll run it. And so my computer is a bit faster than the one Daniel was working on. Let's see. Yeah, here's the book. And it says 1, 2. So for 1,000,000 times, it took 6 milliseconds. Am I getting to 1,000,000 times? So for mine, 1,000,000 times took 3 milliseconds. I'll run it again. So 1,786. Daniel gets, oh, so Daniel runs it even a little bit further than that. So I'll do exactly what Daniel's doing. You'll notice on my screen, I don't know how well this shows up, but it keeps on repeating itself. And so the reason I do that, I'll show you something right quick with this run as an example. So here's one stack. And it goes 0, 8, 73, 864. These are all in milliseconds, right? And then it goes 0, 6. Instead of 8, it says 6. and 19. Ooh, there's a 5, there's a 4, there's a 7, there's a 4. What are we looking at? And so the example Daniel's trying to make here is our analysis predicts a linear time complexity for this loop. As shown in the sample output, when the input size increases 10 times, the runtime increases roughly 10 times. This execution confirms our. So I'm not going to say that our execution confirms the prediction. What I'm going to say is our data supports. So our data doesn't suggest that our model is wrong. The reason why I don't want to say that it confirms it, lots of things can go wrong and lots of crazy things can happen. And the reason why I don't want to say it confirms it, look, in 10 different runs, I get essentially 10 different times for how long everything takes. So if we want to just look at the, typically when you're timing a function run, you run that function multiple times and then you pick the best time. And so here we have a runtime of 4 milliseconds for 100 million. By comparison, Daniel was getting 61. So here for a million, we get 0 consistently, and Daniel was getting 6. And then we're getting, let's see, 79, 71, 89, 73. So it looks like 71 was the fastest. Daniel was getting 610. And then for, let's see, what is that? 1, 2, 3, 1, 2, a billion. Daniel is taking around 6 seconds for us to complete a, let's see, is that a billion? 1, 2, 3, 1, 2, 3. Yep, that's a billion. At its worst, it's taking a second. 822. So less than a second to do a billion, whereas Daniel is taking about 6 seconds to do a billion. Okay, so the reason why I wanted to show you that, when we run this code multiple times, we get multiple results. And what I typically do is I take all of those results, I drop it into a nice, easy to work with environment. Because I get lots of data, and then I sort that data, and it makes it easy to see, hey, those are all the same, all the same. And it just makes it easy when everything is grouped together nicely to see, here are the slow ones, here are the fast ones. And it just makes things a little bit easier to work with. And then if you need to, if you've got so many data points that you can't necessarily easily see that, a spreadsheet has built-in sorting functions as well. So it also helps you make nice little tables. And so, yeah, this is linear time complexity, and we've got several data points that we plotted for that, and we can see that for a linear complexity function, as we do more operations, it takes longer. Cool, linear growth. But what this plot also shows is, in general, some runs might be faster, some runs might be slower, but for a smaller batch, it's going to take, in general, less time. A medium-sized batch is going to take, in general, a little more time, and a large batch is going to take even more time. So that's the advantage of looking at a scatter plot. What can make these things take longer time? Your operating system might decide that it needs to do something. It might, you might have had a nice memory location. You might have hit the memory in a nice way the first time. You might have had other things going on some other time. But in general, that's why you run it multiple times, because odds are you're going to have at least one good run when runs are relatively small. Now, part of the reason why I had this tuned down, the next example Daniel gives in his book says, hey, what if we've got a loop nested inside of another loop? He said, all right, well, for this time, we're still going to have that same time constant, but then we're going to do it not only for the first loop, but that every iteration for that first loop inside the second loop. And so this is n squared. This is called quadratic growth. And so I'm going to dial back my algorithm. Let's do 1, 2, 3. Let's just run it up to 1,000,000 times. Oh, have to get it on the right one. So we're no longer going to do the linear. Now we're going to do the quadratic time example. And you can see quadratic time, every time we multiply this number by 10, we'll see a growth of about 100. I've already ran this analysis before. Let's see if I've got it. There we are, quadratic time example. And I said, give me a range. What's my best and what's my worst? And so we can see that as we multiply by 10, we're multiplying the time that it takes in milliseconds effectively by 100. And so here's our second linear time example and our second quadratic time example. Again, multiply one side by 10, multiply the other side by 100. So the concept is quadratic time basically says, as this one parameter, as this one, maybe it's the input, the data size input, right? As this grows to where it's infinitely large, significantly larger than everything else, how is the time complexity going to change? And there's, in the text, they talk about, bring it back up. They've got a few more examples, and I tried to work through all of the examples. They go through and they analyze the binary search, the selection sort, Tower of Hanoi problem, and they talk about these things. They talk about, hey, if you're going to do a merge sort, which they discuss in chapter 23, that's n log n. And so you can go see what that looks like. If you're going to do the selection sort, it's on the order of n squared. And so they talk about some of these things. You can change your growth rates, and they plot it. And basically what this is, it's a way for you to think about, okay, how is this going to change? Now, one of the things that we were looking at was for our algorithms class was this concept of a merge sort and a quick sort. And so I wanted you to research the algorithms and then implement them. And Daniel Lang, if you go here, he's got the algorithm. So he's got insertion sort, and then we've got the bubble sort. And then if you keep rolling, we have the merge sort. And so this is the algorithm. And essentially what this does is it says, hey, take your set of numbers and split it, right? And keep splitting it until everything is broken down into one number. And then what you want to do is you want to merge them back together. How do you do that? Well, compare the two. If the first number is smaller than the second number, then take the first number, then the second number. However, if the second number is smaller than the first number, then take the second number and then the first number. And they actually give the code. And I will admit, I was able to just copy this right out of the book and paste it right into the editor, and it worked great. And so again, I like to repeat all of my stuff. So I set that up. Let's just walk through the code right quick. I said, here is my main method working in Java, so it's main method, not a main function. Giant comment, and I said, all right, I'm going to use a test fixture object. This is just a place for me to handle all the details. Then I print off my header, and then I print off, let's see, let's make this a little bit smaller. So I'm going to repeat this exercise 10 times, and you can see I've got my little header. It's array size, merge sort with the array, quick sort with the array, merge sort with the list, quick sort with the list. And then I can say, all right, how many times do I want to repeat it? That's just a constant. How big of an array size do I want to have? And that's just a constant that I change so that I can play with it and get some data. All right, then I say, all right, time to get this done. The first thing I do is I make a new starting array. And this is just whatever size I set my array size to be. And then I go ahead and I fill it. And we're not going to talk about that right now. We're just going to glaze over. You can know that I fill the array, the starting array, using fixture.fillArray. This is a custom function that I created, custom method that I created for myself inside the object test fixture. Now, one of the things that I wanted to look at, and I read this in the algorithms text, this is the Richard Neapolitan 5th edition, Foundations of Algorithms. He was saying that, listen, if you do this with a linked list, you're actually going to get different results than if you're doing with an array. So I said, all right, let's go ahead and set up a linked list. And then I said, copy the starting array to the starting list. The thing, I understand that I'm a bit of a simpleton, but you can look at that name and you know what that method is going to do. So give us a little more room to look at here. So I make a copy for merge sort. And again, I just create an array, and then I've got something in the test fixture to go from the starting array to the merge sort array. By the way, I commented these out, but I left print statements in my code. The code is listed in the PDF that I showed you on the in the modules for the Canvas page and in the course syllabus. If you don't trust the code, which I would not recommend anybody trust, I've seen my code be wrong so frequently I never tell anybody to trust my code, but if you want to verify and print some of the things off, I would say make the array size smaller and then go ahead and uncomment some of those print statements. So anyway, I make a merge sort array copy, and then I make a merge sort list copy, and then I make a quick sort copy, and then for the array, and a quick sort copy for the list. And then I do sort with merge sort for the array, and it's the same exact structure that Daniel showed me in the previous chapter. Start the time, current time in milliseconds, end the time, current time in milliseconds, and then just print that off. So I did that for a merge sort and a quick sort, both on the arrays. And then I did that for a merge sort and a quick sort using linked lists. So this is how I created the linked list. The thing that is interesting, okay, we ran this on the same array size 10 times. Our merge sort, and this actually looks cleaner if you, part of the structuring of my print statements is then you can just copy it and come right into a document, you can see it. Anyway, I've done this analysis before, and what I do, I just sort it for the shortest time, and I pick the shortest time. So we could actually, if we wanted to, we could insert a new row here, and we'll say 5,000. And so the shortest time on 5,000 was still 0, 0, oh, into 0 there. And then 168. Yeah, I think 168 will do there. And then on this one, 903. Yeah, 903. So 900, almost up to a second already, just a little over a second for doubling that. And so it's not an exponential growth, it's a logarithmic growth, meaning it's growing slowly, not quite exponentially. And so that's kind of what we had expected from our big O notation analysis. But what this shows is, if you're going to do merging, if you're going to do sorting on an array, it goes really fast. Using the exact same data, just in a different format in a linked list, significantly slower. So anyway, I thought that was interesting. My test fixture, again, you can see I did a lot of copy and paste. Therefore, I was probably doing something wrong, and there's probably a more elegant and efficient way to do this whole process. And so I didn't take the time to refactor that and think that through. But in the end, you get a set of results. And I cherry pick the best runs out of those results, and those are the results that I show. And that's what I have in my notes in Big O notation. I have the tables showing what the time is in the milliseconds. I have bits and pieces of the code as the code grew, kind of talking about what the algorithm is. And, you know, big O of n squared, it's quadratic algorithm, time complexity. That's all from Daniel. And so I encourage you to go take the time to read Daniel's chapter on that. But I also have the code in there for how to do merge sort, how to do quick sort. And then I have the code for quick sort and merge sort. And then let's see if I mention it here. If you keep going down, I do linked list runtimes, and I show the results that we had from before. And so I also give the code in the PDF. The big concept here is Big O notation gives us an idea of how these things should grow when our problem set gets infinitely large. That's why they call it asymptotic analysis. And the concept is Big O says, let's not worry about how long it takes to load stuff in a, do memory reads or something like that. If we've got an operation like a multiplication or something like that, however many times that we need to do that, that's called some constant time for that iteration. And so if we've got n iterations to do, it should take n time. If we've got n log n, like merge sort, it should take n log n time, and we should see kind of a, not quite a quadratic growth, not a linear growth, somewhere in between. And I feel like a lot of the books do a good job of talking about that. The Ken Rosen book on discrete mathematics talks about Big O notation. The Richard Neapolitan Foundations of Algorithms talks about it. Algorithms for Dummies talks about it. The 12th edition has an appendix on Big O, Big Theta, and Big Omega. This is an interesting topic for computer scientists, because actually anybody that has to solve problems with computers, because it kind of gives you a feel of, all right, if I try to go from this little textbook example that I have, and I try to grow that to where I'm dealing with a significant data set, how is the performance of this algorithm going to change as my problem set gets larger? So with that, friends, I hope this helps you understand a little bit more about Big O notation. Big O notation does not tell you how fast it'll run on your computer, because your computer, like the difference between the computer that Daniel Lang used to get his numbers, my computer, I think, is like 10 times faster. It's not necessarily going to tell you how hard it is going to be to program. It's not going to tell you how well the algorithm is going to work using different types of data structures. But what it will tell you is, all right, using the data structure that you have, the computer that you have, as this problem gets bigger, this is how you can expect your time complexity to change. And so it's a useful tool and helps you picking between different algorithms. But in general, rules of thumb that I try to live by, if your language has something built in to do the process, normally that has been optimized for that data structure. So we were seeing that a quick sort was faster on an array, and a merge sort was faster on a linked list. Well, there's the sort function built in for the array. There's sorting built in for collections. Use the ones that are built in. First of all, you don't have to write them on your own, and it did take time. And I will tell you, when I was converting from an array to a linked list, I made mistakes in my code. And so that's why I've got so many nice print statements in there. That was helping me figure out, okay, what is the algorithm doing and what is it that's going wrong? So I left those in there, and if you want to play with that, you can. So with that, Big O notation, very useful, helps you understand kind of the big picture, how's this going to go for the environment that you're working with as that environment changes to larger problem sizes. All right, friends, I sure appreciate this time with you. I hope you have a wonderful day. And if you have any questions, please do email me. It's jeremy.evert@swosu.edu. I am Jeremy Everett, and I am a computer science faculty at Southwestern Oklahoma State University. Thank you all for your time. Have a wonderful day.